Today I'm going to talk about the optical method, which is called the photoelastic method. So if you have now, if you want to use the photoelastic method, you can do it for both transparent materials as well as opaque materials. When you make a composite, so even if you use, let's say, epoxy or polyester as your polymer matrix, you add glass fibers. Now glass is transparent. The polyester or epoxy is also transparent, but when you add them together, they become opaque. Of glass and the refractive polymer are different, so there's too much light scattering, and you do not get light transmission through the sample. Now, so you can use something called photoelastic coatings, and so to figure out the stress state on object through the use of these coatings on opaque material. It gives surface stresses. It doesn't give the true thickness stresses. That's why you would use the transmission photoelastic method. Okay, and then that's what I'll be talking about. So that gives you an average value of the stress through the thickness of the sample. Okay. So that's where this transmission photoelasticity comes in. But the problem with that is that you need transparency. Now I said that the composites are opaque, so they are not transparent. And the main reason is that you do not have a matching of the refractive index. See, if you have 4 or 5 different phases in the material, all having the same refractive index, then optically so the light which is coming because you have the same refractive index. Okay. So transparent model composite then allows also inspection of damage through the thickness of the material. So if you have transparency, then I not only find we see visually any crack formation, which how the crack and how they are forming. Okay. So that's why this is the advantage of having this transparent composite. So that's what we actually did. We tried to make a transparent composite. Okay, and so we have fiberglass cloth, so woven fiberglass, just like cloth. And so we added 7 layers of that. The total thickness of the composite is 3 by 16 inches. And the fiber volume fraction came out to be about 25%. So, and the transparency we attained by chemically matching the refractive indices of the matrix and the reinforcement. Okay. So we tried to do this, and it's not part of what I'm going to talk about today, so I will just say that we actually modified the refractive index of the polyester matrix so that it's almost equal to, we can hardly ever get it exactly equal. So we got it almost equal to that of the fibers. Okay. Now, some people have also tried to modify the refractive index of the glass fiber itself, and they have done that by trying. So when you make glass fibers, what you do, you take a tank, you melt the glass, and then there is a very small like a platinum or tungsten nozzle at the bottom, which has a very small hole. Okay, and as soon as it comes out, it begins to solidify. So you take that fiber, put it on the roll, and then slowly pulling it, and it keeps pulling the glass, molten glass out, and it keeps solidifying. Okay. Now, if you take that glass which comes up, pull it at higher and higher rate. You are actually trying to stretch it while it's, and then you introduce certain fiber which tend to change the refractive index of the fiber. So, but that method was also not very successful. So this method which we followed go the other way, match the refractive index, change the refractive index of the polymer and match it to the glass. That worked out better. Yeah. And so actually we also got a patent on this. So this is how it looks basically. That if I look at this structure, this is, then I took this is just right outside the lab, so I just took one picture with a camera, and then this picture is taken by putting that transparent fiber composite in front. The camera is about here, and you look at the picture on the wall. So this is how it looks. So as you can see, it is transparent, yes, but there is some coloration to it. There's a little blue tinge or hue to it, and there is a little bit of loss of some of the features, a little hazy. There's a little haziness in there. Okay, but by and large, you can still see most of the things that you would see on this side. This is the if you put the this is by putting the composite sheet right on top of a cover, the cover of a book, right on top, and then see. That always works out to be a better, it apparently gives you a better transparency. You put it away, like in the middle, not on top. So this is what we are then going to do. So why we are doing this? Because we are, composites are used in critical structures like planes and other things. We want to know the mechanical behavior of this composite with cracks present in it. Also important to know the behavior of bimaterials with interface cracks. Okay, so that's what we are trying to do. Now, whenever you have working on, okay, so you do it, and there's a lot of damage inside the. How do you now know what is the extent of damage? You can see anything. So how do you see that? What doing anything to see the extent of damage inside? Ultrasound or CT scan or something like that. Yes. So that's another way to do it. But if you have a transparent composite, you don't need to do any of that. You clearly see it. And also by sometime by you will also see that you can do a few other things, okay, in terms of visualizing the extent of the damage and other things. Okay, so this I think skip this. So the basis for photoelasticity is that the material changes its refractive index when subjected to stress. Okay, that's the basis for photoelasticity. If I have material, if I use a composite polymer composite, if its refractive index when stressed, then I cannot use this method. Okay, so the photoelastic method is based on this principle here. At different refractive indices in a material, direction also means different speed of light in that direction. So that's another thing. Refractive index of material. So lengths of light, that means different colors also travel at different speeds. So we have this, so then the light waves undergo relative retardation when traveling through a stress model. So what does that mean? So that means that, let's say this frame you see here is a composite or whatever, any material that is going to change its refractive index depending upon the state of stress at that point. So the state of stress is best defined by the principal stresses, okay, sigma 1 and sigma 2 in that plane. So we can then say that, so let's say at this point here, I have some stress value sigma 1, sigma 2. Here I have some other sigma 1 prime, sigma 2 prime. In the middle I have sigma 1 double prime, sigma 2 double prime. So and so on. So every point has a different state of stress. There may also be contours of stress which have constants. Okay, so I might have sigma 1 which is constant along a certain contour, sigma 2. That's fine. So what happens then? So when you have light, and I'll show you that in a minute. So if light refractive index is different at different points, then what's going to happen? We saw last class, you have a crack. In the vicinity of the crack, the stress field is different. Far away, it's uniform. Okay. So in the vicinity of the crack, because of the large gradients in the stress field, you can have from point to point. So if a collimated beam of light is coming through, point will come out on the other side a little different because of the difference in the refractive index. Okay. So it will, if this light beam is one below that, will go at a slight angle this way, other way. Okay. Likewise, the whole field of view have rays of light which are coming out with slightly different phases. You can imagine. So what happens then on the other side is, so all of these light beams which come out, these light rays, then they combine on the other side or they undergo interference. So they come and they undergo interference. When they undergo interference, they create certain bands which are called fringes. Okay, so you see those fringes. Now it turns out that these fringes are contours of constant maximum shear stress, that is the in-plane shear stress, which is related to the difference between the in-plane principal stress. Okay, so that's what the whole idea is, and this is achieved through experiment. So this is what it looks like. This is something called a polariscope. Okay? So a polariscope has an analog, let's say this is the light source. So this light source can be either monochromatic. Generally we use sodium vapor lamps. Okay? So it's one wavelength here. So then this is a polarizer here. So what is a polarizer? So light has vector, electric vector going in all directions. It's rotating. The polarizer makes the light vector come out in the direction of the, it's either vertical or horizontal, or however you set it. Okay. So in this case, you get polarized light out. Then there is another polarizer type of thing here, but it's called a wave plate. So it introduces a 45-degree, so it comes out vertical, the polarization act. It introduces a 45-degree shift. Okay. Then you have the specimen here. This is a parallel beam of light, and maybe about in this area. Now when it comes out on the other side, introduce the 45-degree rotation. We undo that by this one then shifts it the other way, or to the other side. Okay, by instead of plus 45, then you do minus 45. And then there is another polarizer on this side, which its polarization axis the same as this polarizer, the first one, or so when you keep it in the same phase, it's called, it gives you a bright setup. If you put it on this side, it's a dark setup. So the light coming out is reduced. So both are okay. You can use one or the other. So this just shows you the same scheme of things that I talked about. And at any point you have sigma 1, sigma 2 as your principal stress at that point. So every point then is affected like this. Now, I cannot go in more detail here. It takes a long time. So, but you can read up, even if you do Google transmission photoelasticity, and you Google something, and that will tell you, or you do isochromatic fringes, that will also bring up. So you can read more about this. So this is what it looks like, again that same picture. So this set here, this round thing, behind that is the light source, and you have the polarizer and the quarter wave plate in this side. In the middle we have a sample, and on this side again we have another quarter wave plate. And so I put two samples in this load frame in the middle. I put two samples. One has a hole in it, the other has no hole in it. Okay. So this is a homalite 100 with like a polyester. Why we use homalite 100 here is because it has effect. So if I take a glass sheet with a hole in it, I will still see some fringes, but I'll see very, like you see this nice pattern here, you will paint few fringes. Take color and then good way of making samples to see your refractive unit. A good way to explain the effect of, and you can press around it. Okay. Whereas on this, which is uniform plate, it's a uniform stress. So nothing. I have gradients in stress. So all the light beam is going out there, going slight direction, and then they are interfering on the other side to produce these patterns. From here, effect of the unit stress field, so you don't see anything because all the going out the exact same phase. So that's what. Okay. So I have this sample here. This is called single edge notch fracture specimen. Single. So this is the edge. I make a crack in the edge, in the middle. Sometimes you can also make center crack specimen. So I put fibers here. See, there's one fiber here, one fiber here, one here. So they are so far apart. Okay. So they are far apart. Why? Because I want to study how this crack, when it is traveling, how does it interact with one fiber? If I put 30-40% volume fraction, then I cannot do that. So I want to do some basic understanding of how this comes down and travels through here. Okay. And we had put some eddy current transducer on the back side here to be able to see the crack opening displacement. So you need not worry about that. So again, this is a photoelastic material. that fracture specimen is made out of polyester, which is very similar to Homelite 100, which is another different type of polyester. And I can then see very similar fringe patterns. So the crack just started here, and so what this is showing us is, as time progresses, so this is at 32 microseconds after the crack started, okay, and then this is 60, this is 126, 131, this is 150. So the crack is moving down that path. Look what happens here. So these are the single fibers here. The crack is going down this. This is the state of the stress field around that tip of the crack. So I can use this stress field actually, and I can calculate the stress intensity factor that we talked about yesterday. The other thing that you can see here is, see what is this dot here. I'm seeing some small fringes develop here. So that fringe is giving me the length of debonding of the fiber. So the debonded fiber is at this point right now. So at the debond end of the debond, there is some stress field, localized stress field. So I can see the rate of debonding of this fiber pattern also. Okay. Now, what if there was no debonding at all? Versus, in this case, I have this length that is debonded. What will happen if there was zero debonding? Also notice that this fiber is still intact. It has not broken yet. And my crack has already gone so far down. Okay. That's another thing that we found, that fiber failure actually happens after a long time after the crack has bounced. Okay. And that is why you get a damage zone behind it, and what else you get? Fiber bridging. So fiber bridging means you have a crack on this side, you have a cracked surface on this side. Between those two, there is a bridge, which is the fibers. Okay. So if there was, so over this length, over that length which is debonded, that debonded fiber is stretching now. Because here and here, I am pulling apart, and this part is all solid material, and this fiber is bridging that gap, and it is taking a load. And since that gauge length, so that becomes the gauge length over which the fiber is stretching. Okay. So what is the strain? Is the change in the length of that fiber divided by the debonded length. Okay. Divided by the debonded length. That is the strain in this fiber. So if there is zero debonded length, what is the strain in that fiber? Huh? Sorry? Infinity. Infinity, right? So what will happen? It will break right away. It's not going to stretch anymore. So what happens to that composite, which has no debonding at all, perfect bond? That composite is very weak. Once it starts a crack, it breaks like a brittle material. So some debonding is very essential, okay, as you see from this picture. After the cracking was all done, the specimen broke, then you look at around, because now I only have one fiber here, so I can look around and see what happened to the fractured surface. Okay. So this one is like one copper fiber here, this is a glass fiber, and this is a nickel fiber. So we just tried metallic fibers and glass fibers. Okay. So you see, when you have a thicker fiber, these are copper fibers were a little more thicker than the glass, and then we get very rough surface, and we get a pattern like this. Okay, and so when we see these ridges like that, what is that telling us? That the crack did not propagate continuously. It's like fatigue. You know, in fatigue you see these ridges, you know, that thumbnail shaped marks like that. Why do you see those? Because the crack moves, stops, moves, stops, moves and stops. So every time it stops, it gives you that little ridge. Okay. So it seems like the same thing happened here. Even though it's supposed to be a dynamic, continuous propagation, but as it hits this fiber, it breaks into two parts. It seems to, for a very small instant of time, it seems to stop and go before it starts, it goes all the way through. Okay. Look here. So we were able to capture one picture where the crack came, and so in this high-speed camera we were using, you see that this is the fiber and this is the crack front. See how it is divided into two crack fronts. So, and these are the fibers. There's one fiber here, one here, here. Okay. So this is how it seems schematically the crack is propagating around the fiber. So it comes here, full crack length. It divides into two parts. It keeps, now it travels a little faster here than in the middle, okay, because you have plane strain conditions on the outside compared to the inside. And then eventually it again joins up, and then it starts moving as if there is as before. Okay? And that's what you see also in here. Okay. All right. So now I have a composite which has a high volume fraction. Okay. So my high volume fraction is about 25% volume fraction. It's transparent. I put a crack in it. Now this is static. Okay, it's not moving. So, and then I am pulling from here, and I see all these fringe patterns here. So I know the state of stress around the crack tip. Okay. And then I showed you last time that very close to the crack tip, a little circle here, we don't want to take data from there because that is too close to the crack tip. The stress state is not planar, it is three-dimensional. Okay. And so this area that we don't take from is this diameter is equal to the thickness of the sample. Okay. This circle here is about 4 times the diameter is 4 times the thickness. Okay. So we believe that outside of this, it is too far from the crack tip, so it is not the singularity dominated zone. Okay. So it goes too far out. It is dominated by the far field stresses, not by the crack tip stresses. Okay. So then what I do, I take, so I have this fringe, I have this fringe, I have this one in the middle. So I take data points from here. So I make a grid, and on each I say that, okay, so this is the 0 order fringe, this is first order, second order, third order, and so on. So I take data points, and I take the coordinates of the point and the order of the fringe. Okay. Then I have to go through this analysis. So what is the state of stress at the crack tip? And now this is not an isotropic, it's an orthotropic material. Okay. So there is an Airy stress function for a notched orthotropic material, and you can find this from some previous literature. So we got this from another paper. And then, so this is the Airy's function, which is rewritten Then we again use that complex series solution for the complex function, and we introduce a minus half in there to account for the inverse singularity. And then once I know the stress function, then I can find sigma x, sigma y, sigma z from this, from the Aries function. And very similarly then, the very first term in that series has the minus half relationship in the exponent, and that's related to the stress intensity factor. This is the state of stress. This is the final stress field. Stress is here, and then I still have not combined it with the optical part, which is the photoelastic part. Okay, so I just have the stress field in the composite around the Kraken. This is called the stress optic law. Okay, the stress optic law says that this is the order of the fringe n. That, so I'm showing you those fringes. So zero order is where there is zero stress around the Kraken in some region around the tip. Then you keep going up, first order, second order, third order. So this is sigma 1, sigma L by F. Now F here, this FL, FT, FLT is called the material's photoelastic constant. Okay. And there is a method to find these. Okay. So you can find these. Then I have tau LT, sigma T, sigma L. So if it's a unidirectional composite, sigma L is the L direction in the direction of fibers, T is the transverse. Okay. And these are the fringe, photoelastic fringe constants here on the bottom. So then what I can do is now, and H here, that's the thickness of the specimen. So I can then put in my stress field here, sigma L, sigma T, tau LT into this expression, and I get something like this. Then I know the fringe order at a point. Once I know at a point, I know like Z is equal to R e to the minus I theta, so I know the R theta location of the point. I know the fringe order, I know the thickness, so I know a lot of things here. Okay. And then it's not an exact equation. So there is some stress intensity factor which is the exact value. But I am trying to find it using that fringe pattern. And I am finding it using so many points. So I only need maybe 1 point. I can solve that equation with just 1 point. But that may or may not give me the right answer. So I do many points and then do an over-deterministic least square method to find and minimize the error. Okay, so that's what we are doing here. So all I did was, so in this expression, I now define an error function. So I just took the right-hand side minus the left-hand side equal to G. If it was exact, then my error is 0. But I have so many points, so I go through a least square solution here, try to minimize the error, and then I end up with, we calculate these constants A n, B n, and everything from that scheme, and come out see, so there are all these so there were all these constants in that. There was where is my stress field here? Oh, here. So I have this coefficients A, B, B1, B2, A1, A2, and so on. Okay. So those constants then I find also from my least square analysis, and I come up with all of these, and then A1, the first term, which is related to the very first term, is then related to the stress intensity factor. Okay. So, and that is we gave you here, like K1 is equal to square root 2 pi A1. So that's the way you can find the stress intensity factor for all of these moving cracks in composite material, or they can be dynamic cracks, just like I showed you for that single fiber thing. If I have a high-speed camera, I didn't have one high-speed camera, so I was not able to do for these transparent composites, but you can do that if you can take pictures as the crack is moving. Yeah. As I said in the beginning, if you still want to use photoelasticity, you can put photoelastic coatings on the top. Okay, but the coatings give you errors because they are only the output you get from the coating is based on the surface stress. Here I am doing through thickness measurement, so it's a little better in that sense that it's an average of the stress field through the thickness. And if it's a plane stress case, then the average variation through the thickness is very small. Okay. So this is more accurate in that sense. So now, so what we did again was, so I found this method. All right. So once I calculate the K value using this over-deterministic least square method, using those fringe patterns, then I forget about everything and I know the K value now. I know all the equations. I know the constants A1, A2, B1, B2. So I put them back in the equations and try to regenerate the fringe pattern. Okay. So this is then, so what we did was, so this is my experimental pattern. Okay. This is the regenerated pattern with 5 terms from that series solution. This is again 5 terms. This is 3 terms. Okay. So we try to regenerate these patterns and see do they match up or not. If my solution for K is correct, then these patterns should match up. Okay. This is for crack length to width ratio of 0.25, 1340 newtons load. This is my fringe pattern. And this is for 3 terms. This is for a 5-term solution. This is for a 5-term solution, but a smaller annular region. Okay. And this is a bigger annular region. Okay. So you see that this one and even this one, actually this one matches better with this than this one. So qualitatively they are all matching in this right now. There's not too much difference between this and this. Okay. And this is again for a longer crack, 0.55 A by W and lower. So I get very weak type of fringes, but you can see that the fringes are bending backwards a little here. They are bending backwards a little here too. Okay. Here I get this fringe. Here also I get this. But in this I'm getting in the middle also. So it's not representing the stress state that well. So a 3-term solution seems to be the best solution. Okay. So anyway, so then let's look at quickly the interfacial fracture. Okay. So now what I'm going to do is, let's see if I can switch a little. So, okay. So here I have one plate on the top, another plate on the bottom. I join this with a glue, some adhesive up to here and up to here. In the middle, in this portion, I put a little Teflon, little very thin Teflon sheet, okay, so that the 2 cracks, the sides, the plate, they don't join, okay, so they are separate. So I create an artificial crack in this. So this is like an interface with a crack in it. Okay. So then if I pull this, if I'm now pulling it in the vertical direction, these are the crack tip stresses you see. This is at an angle. I see these stresses at the end. This, what you see, is probably due to some rubbing. It's creating some stress there. So this is the type of sample that I have a upper half, a lower half. You join one part of it with an adhesive and leave a crack or an unbonded region, which is the crack. Okay. So now to find these stress fields, so what do I need to do? I need to find the stress field around the crack tip. And if you can read that, that's the stress field. Okay. Sigma x, sigma y, tau x, y. And then it has all that same series solution we are using again, and combine it with the stress optic law, okay, and do the exact same thing again. You have a lot of points you get from the field of view around the tip of the crack, but avoid the center portion, diameter of one thickness. Take points up to a maximum of 4 times the diameter, 4 times the thickness of the sample. And put it, again put it in this polariscope that I showed you before, and then this is the student who worked on it, so he always liked to show his face. And there are some guidelines given as to how we actually made the sample, so you can read those if you want to make some samples. They'll give you some guidelines here. And then, so all of these different types of surfaces and different types of interface combinations he looked at. He also tried to do a disk with a crack in it. Okay. All right. So this is exactly what. So we tried different things. This is an isotropic, just a pure polyester plate. On the bottom is a composite plate, and in the center you have that interface crack. This is how it looks like. This is a metal plate, an aluminum sheet with the composite patch. Okay, that's what you use a lot in aircrafts. You do composite patches, and you glue a composite patch on top of an aluminum crack. So that's what this is. And then again, you start doing the exact same thing. So you see, so we took points from the center of the fringes here and here. We took points from the center of the fringes. So if you take points like this, it gives you a better result, rather than taking randomly everything. And we go through an over-deterministic set of equations solved in a least square sense. Again, same thing. And then I try to regenerate my fringes to see if the output I got, how closely it matches with. So for example, here, this is the actual fringe pattern we saw. This is the regenerated fringe pattern. Okay, this is for the lower half. And then we got the K value and the energy release rate. Now it is a composite, so we are getting K1 and K2. Okay, there's some degree of mode 2 stresses in there. And then there are all these different combinations. We try to play around with taking 2 terms, 3 terms, 5 terms, which one matches better. So we found that taking either just 1 term or 2 terms comes out to be better in this case. Whereas in the isotropic case, up to 3 terms is okay. But in the composite case, taking 2 terms is the best scenario. So anyway, there are all these different pictures you can see. Okay. Now, we also try to look at what if I mislocate the crack tip. So everything there, what you saw, is based on pinpointing where the tip of the crack is. So in an isotropic material, you can get that quite well by looking at the fringe pattern. All the fringes are moving in and joining at one point, which is the tip of the crack. But in a composite, it's a little more fuzzy. It's not very easy to see where is the exact crack tip. Okay. So, for example, let's see, like this here. See, so I see this big dot in the middle. So somewhere here is the crack tip, but I cannot see more clearly what it is. So I can go off by maybe quarter of a millimeter or half a millimeter error in my estimation of where the crack tip is. So the actual crack tip, all the fringes are actually joining at that tip. Okay. So then what we did was we tried to do this, that here, effect of mislocating the crack tip. So here this is x equal to 0, y equal to 0. So let's say that is the exact fringe, exact tip of the crack. Then I try to regenerate my patterns by assuming a grid of crack tips. Okay. So what I'm doing is basically this. So if this is the tip of the crack, so I assume I take a little grid around it. So I said this. So I take some grid points, and I take this to be 0.25 millimeters. So I search for the crack tip basically by regenerating the fringes, assuming all of these points here. Okay. So wherever my fringe pattern, the regenerated pattern, matches the best with the actual pattern, that I say is the crack tip. Okay. So you see here, if I go half a millimeter off, or what is that, 1 millimeter off, this, it looks really bad, right? This one looks a little better here, but this is -1, -1, and then all of these look a little different. So ends up the best visually what you see, then you can say that that's the location. So that's the other advantage of this method. This is what we did for increasing the number of terms. So this is 2 terms, this is 1 term, this is 5 terms, I think, is it? 3 terms here. So here you see this is the actual pattern, and this looks really odd. It looks very different. Okay. So you can also try to work around like this by looking at the sensitivity to number of terms. So that's in essence then another way of looking at fracture in materials. So you can either use strain gauges, which is just giving you the stress intensity factor, but if you use this transparent composite method, you can also see fracture zones, you can see debonding, you can still calculate the stress intensity factor and look at the general state of stress in the material. Okay. All right. Any questions? Okay. Then if no, then we'll, I think, supposed to take a 10-minute break. You want to take a break?